From ancient stone arches to today's engineering marvels, bridge construction has always pushed human limits and discovered the secrets behind the world's most iconic bridges. The construction of two iconic cable-stayed bridges in Vladivostok marked a turning point in the city's development ahead of the 2012 Asia-Pacific Economic Cooperation Summit. Among them, the Russky Bridge stands out as a record-breaking engineering marvel. Spanning the eastern Bosphorus Strait, it connects the mainland to Russky Island, the summit's venue. Built between September 2008 and July 2012, the bridge features the world's longest central cable-stayed span at 104 meters and reaches an impressive height of 324 meters, making it the second highest bridge in the world. Engineers overcame harsh weather conditions such as strong winds, powerful waves, and heavy ice to complete this challenging project. Equally significant, the Zolotoy Bridge crosses the Golden Horn Bay, linking the city center with the Turk and Cape area. Construction began in July 2008, and the bridge opened in August 2012, greatly reducing travel time across the bay. Together, these bridges not only transformed Vladivostok's transport system, but also became enduring landmarks, symbolizing the city's modernization and strategic importance in the Asia-Pacific region. The construction of the cable-stayed bridge to Russky Island over the eastern Bosphorus Strait in Vladivostok stands as one of the most ambitious engineering projects ever undertaken in Russia. Known today as the Russky Bridge, this remarkable structure has earned global recognition as the longest cable-stayed bridge in the world. Completed in 2012, just in time for the Asia-Pacific Economic Cooperation Summit, it has become both a vital transportation link and a symbol of modern Russia's capabilities in civil engineering. From the very beginning, the project was envisioned not only as a way to improve connectivity, but also as a statement of progress and innovation. Before the bridge was built, access to Russky Island was limited to ferry services, which were often affected by weather conditions and scheduling constraints. The need for a permanent, reliable connection became especially urgent when Russky Island was chosen as the site of the Far Eastern Federal University campus, which was to host delegates during the APEC summit. Thus, the Russky Bridge was conceived as both a functional infrastructure project and a showcase of Russia's technological achievements. In terms of scale, the bridge is truly extraordinary. With a total length of 100 meters, or roughly 200 feet, it stretches across the wide span of the eastern Bosphorus Strait. Its most notable feature is the central span of 104 meters, which makes it the longest of any cable-stayed bridge in existence. Supporting this immense length are two towering pylons, each designed in an A- shape that rise to a height of 325 meters. Or 1066 feet. These pylons are among the tallest in the world, ensuring the stability of the structure and providing the necessary support for the vast number of cables that extend outward to hold the bridge deck. The design of the Russky Bridge is as functional as it is visually striking. The cable-stayed system was chosen because it allows for longer spans than traditional suspension or beam bridges, making it ideal for crossing the eastern Bosphorus Strait without requiring numerous support pillars in the water. This not only enhances the bridge's structural efficiency, but also creates a sleek and elegant profile that has become an architectural landmark in Vladivostok. The deck itself accommodates 4 lanes of traffic, ensuring smooth and efficient travel between the mainland and Russky Island. When it came to materials, engineers employed a combination of concrete and steel, both of which were selected for their strength and durability. Given Vladivostok's harsh maritime climate, with temperatures that can plummet to -30 degrees Celsius in winter and rise to +30 degrees Celsius in summer, as well as the constant threat of heavy ice in the surrounding waters, the structure had to be designed to endure extreme conditions. Every element of the bridge, from the pylons to the cables, was engineered with these challenges in mind, guaranteeing not only safety but also long-term reliability. The purpose of the bridge extended well beyond the APEC summit. While its initial construction was motivated by the need to accommodate thousands of international delegates traveling to Russky Island, its long-term impact has been much greater. Today, the bridge serves as the main link between Vladivostok and Russky Island, providing access to the university campus and supporting the ongoing development of the island. What was once an isolated area accessible only by ferry is now seamlessly connected to the mainland, encouraging growth in tourism, education, and local business. Beyond its practical role, the Russky Bridge has also taken on symbolic importance. It represents Russia's commitment to modern infrastructure development and has quickly become a defining feature of Vladivostok's skyline. Its iconic silhouette, with towering pylons and sweeping cables, has made it a point of pride for the city and the nation as a whole. To further underscore its significance, the bridge was chosen to appear on the 2,000 ruble banknote, cementing its status as a national symbol. For those who experienced the bridge firsthand, the impact is just as impressive. The most common way to cross it is by car, where drivers are treated to breathtaking views of the sea and the surrounding landscape. Cyclists are also permitted to use the bridge, though pedestrians are not allowed to walk across it for safety reasons. From the deck, one can appreciate not only the engineering mastery, but also the natural beauty of the eastern Bosphorus Strait, making the crossing a memorable experience in itself. In conclusion, the Russky Bridge is far more than a transportation structure. It is a testament to human ingenuity, resilience, and ambition. By linking the mainland of Vladivostok to Russky Island, it transformed accessibility, supported international events, and became a lasting symbol of modern Russia. The Osman Gazi Bridge, also known as the Izmit Bey Bridge, stands today as one of the greatest engineering accomplishments of modern Turkey and a milestone in global suspension bridge construction. Rising gracefully above the waters of the Marmara Sea and linking the towns of Hersek in Yalova and Dilovasi in Kocaeli, the bridge is not merely an infrastructural project, but a symbol of innovation, connectivity, and national ambition. Since its inauguration in June 2016, it has held the distinction of being the longest bridge in Turkey and one of the 6 longest suspension bridges in the world. With its total length of 682 meters and its record-setting central span of 550 meters, it has transformed the transportation landscape of northwestern Turkey while demonstrating the effectiveness of semi-prefabricated construction technology, which reached new heights in this project. From the beginning, the project was motivated by both practical and symbolic purposes. On the one hand, the Gulf of Izmit had long represented a natural obstacle to travel between Istanbul and the western provinces of Turkey. Previously, drivers either relied on ferries or circled around the Gulf, a journey that could take up to 10 hours under heavy traffic conditions. On the other hand, the Turkish government sought to showcase the nation's capacity to deliver mega projects of international scale. Consequently, the Osman Gazi Bridge was incorporated into the O5 motorway, a 409-kilometer highway linking Istanbul with Izmir, thereby reducing travel times dramatically. What once took nearly 10 hours can now be completed in only about 4 hours. And trips from western provinces to Istanbul's Sabiha Gökçen International Airport have been shortened to roughly 1 hour. Thus, the bridge was not only an engineering achievement, but also an economic catalyst, and its construction represented an investment of approximately $1.3 billion, a cost justified by the long-term benefits it generated for the nation. In addition to its economic rationale, the design philosophy of the bridge played a significant role in shaping its identity. Engineers and architects were tasked with creating a structure that could withstand one of the most seismically active regions in the world, while also blending harmoniously with the natural beauty of the Gulf of Izmit. Therefore, aesthetic considerations were carefully integrated into the project. The steel towers, soaring 234 meters above sea level, were designed with slender lines that complement the coastal skyline, while the colors and shapes of the structural elements were chosen to merge with the sea and sky rather than clash against them. Moreover, every design decision was guided by the knowledge that the bridge stood above the North Anatolian Fault zone, a region notorious for powerful earthquakes. As a result, safety and resilience became inseparable from beauty and functionality. Equally important, the structural features of the Osman Gazi Bridge highlight its technological sophistication. The total span of 682 meters is distributed across a central suspended span of 550 meters, supported by main cables that stretch from anchorage to anchorage across the Gulf. The deck accommodates 6 lanes of traffic, with 3 lanes in each direction, ensuring that the bridge can handle high volumes of vehicles moving as part of the O5 motorway. Below the roadway, the sea remains navigable thanks to the elevation of the deck, while above, the iconic suspension system provides stability and balance. The steel towers rest on immense concrete foundations reinforced with gravel beds, a design choice that not only anchors the bridge firmly into place, but also allows limited movement during seismic events. This capability to slide slightly in response to earthquake forces represents one of the most advanced features of the bridge, ensuring that the energy of seismic shocks can be dissipated rather than concentrated into destructive vibrations. What makes the Osman Gazi Bridge especially remarkable, however, is the method by which it was constructed. Unlike traditional projects that rely entirely on on-site assembly or complete factory prefabrication, this bridge was built using semi-prefabricated technology, which combined the strengths of both approaches. Large steel deck segments were fabricated in controlled factory environments, where precision could be guaranteed and adverse weather avoided. At the same time, these prefabricated elements were transported by barge to the construction site, where they were lifted into position using floating cranes and secured to the suspension cables. By doing so, engineers minimized the risks associated with working at high altitudes over open water and significantly improved safety conditions for workers. Moreover, the parallel production of deck segments in factories and the simultaneous progress of tower and cable installation at the site allowed the overall timeline to be shortened considerably. As a result, the entire project was completed in just over 3 years, an extraordinary pace for a bridge of such scale and complexity. Furthermore, semi-prefabricated construction guaranteed not only speed but also accuracy. Each deck segment, weighing hundreds of tons, had to be perfectly aligned with the adjacent one to create a seamless roadway. Through advanced welding and bolting techniques, supported by state-of-the-art alignment systems, engineers achieved this precision, producing a deck that functions as a single continuous unit. Consequently, the driving experience across the bridge is smooth and uninterrupted, while the structural integrity of the deck ensures long-term durability under heavy traffic loads. Although construction efficiency and precision were vital, safety in the face of earthquakes remained the most pressing challenge. The North Anatolian Fault had historically produced catastrophic earthquakes, including the devastating 1999 Izmit earthquake, and the memory of such events loomed large over the design of the Osman Gazi Bridge. To meet this challenge, the foundations were designed with flexibility in mind. The steel towers rest on concrete bases that sit atop thick gravel layers which function as a kind of cushion, allowing the towers to slide slightly when subjected to seismic forces. This controlled movement prevents the concentration of stresses that could otherwise lead to failure. In addition, the suspension cables and anchorages were engineered with enough elasticity to absorb shocks, while expansion joints in the deck permit controlled movement without cracking or breaking. Thanks to these features, the bridge can withstand earthquakes of considerable magnitude, making it one of the most seismically resilient suspension bridges ever built. As construction advanced from March 2013 onward, the project unfolded in a sequence of carefully coordinated phases. First, massive caissons were sunk into the seabed to serve as the foundations, which were then filled with reinforced concrete and topped with gravel for seismic protection. Next, the towers were erected, each section prefabricated and lifted into place until the full height of 234 meters was achieved. Once the towers were complete, the main suspension cables were spun from thousands of high-strength steel wires, an operation that required both precision and patience. These cables were anchored securely on both shores and connected by suspender cables, which would later support the deck. Following this, the prefabricated deck panels were transported, lifted, and connected sequentially, an operation requiring both massive floating cranes and meticulous alignment. Finally, the deck was surfaced with asphalt, guardrails and lighting were installed, and finishing works completed. By June 2016, only 3 years after groundbreaking, the bridge was ready for inauguration. When the Osman Gazi Bridge opened to traffic, it immediately entered the record books. At the time of completion, it was the 4th longest suspension bridge in the world, the 2nd longest in Europe, and the 6th in terms of central span length. More importantly, it was the single longest bridge in Turkey, setting a new benchmark for national engineering achievements. This record-breaking status quickly turned the bridge into a source of pride not only for the engineers who built it, but also for the entire country. The inauguration, attended by President Recep Tayyip Erdogan and Prime Minister Binali Yildirim, marked a moment of celebration and national unity, as the bridge was hailed as both a practical achievement and a symbol of progress. Beyond records, the impact of the Osman Gazi Bridge on the Turkish economy and society has been profound. The reduction in travel time between Istanbul and Izmir has facilitated faster transport of goods, more efficient logistics, and greater integration of industrial regions such as Bursa and Kocaeli with national and international markets. Tourism has also benefited, as travelers now find it easier to reach coastal resorts and cultural sites along the Marmara and Aegean regions. The Hong Kong-Zhuhai Macau Bridge is a remarkable engineering achievement and one of the world's most iconic infrastructure projects. Stretching a total length of 55 kilometers, it is the longest sea crossing in the world, linking Hong Kong, Zhuhai, and Macau across the Lingding and Jiuzhou channels in the Pearl River Delta. The system includes 3 cable-stayed bridges, a 6.7-kilometer undersea tunnel, several viaducts, and 4 artificial islands. Designed with a lifespan of 120 years, the bridge was built at an estimated cost of $126.9 billion, with the main section financed jointly by the governments of mainland China, Hong Kong, and Macau. Construction officially began on December 17, 2009, and after years of overcoming complex engineering and environmental challenges, the bridge was inaugurated by Chinese President Xi Jinping on October 24, 2018, marking a new milestone in regional connectivity. The construction of the Walterdale Bridge in Edmonton, Alberta stands as one of the most challenging and ambitious engineering projects in recent Canadian history. It replaced a century-old bridge with a state-of-the-art structure that pushed the limits of modern design, teamwork, and endurance. The project required an international team of engineers, the specialized skills of local 720 ironworkers, and an investment exceeding $150 million. More importantly, it demanded the strength, toughness, and bravery of workers who daily faced some of the harshest weather conditions in the country, with the icy North Saskatchewan River flowing beneath them and winter storms pressing relentlessly. From the outset, the challenges were clear. The centerpiece of the bridge, a massive 1,000-ton steel arch, had been fabricated on land over many months. To install it, the crew had to float the entire structure upstream on barges, position it between the towers, and set it precisely on its bearings. This task required absolute accuracy, as even an error of a fraction of an inch at the base could translate into several inches of misalignment at the top. The risks were enormous. The ice-filled river allowed only a small window of opportunity, and if anything went wrong during the move, the consequences could be fatal. As the workers often remarked, in their trade, mistakes could mean never working again. Before the arch could be moved, crews needed to erect temporary falsework, known as the red iron. Painted in bright red, these steel braces provided critical support, holding components in place until the bridge structure was fully secured. Working at dizzying heights, often 56 meters above the frozen river, ironworkers connected braces while balancing on narrow beams. The danger was real, and many workers recalled close calls being nearly struck by falling steel, suffering slips on icy girders, or recovering from serious injuries. Yet, with nerves of steel, they kept climbing, bolting, welding, and securing each piece. They carried with them not only courage but also pride, knowing their work would endure for generations. The operation to float the arch was a feat of planning and precision. Engineers placed the massive span onto greased skid shoes, allowing it to slide gradually onto the barges waiting in the river. Before attempting the real move, the barges had to undergo test runs without the heavy load. Navigating in shallow water was already a challenge, and repeated dredging was needed to clear rocks and deepen the channel. Even so, the barges often became stuck, halting progress for hours or even days. Tensions ran high, as every lost day brought the project closer to the arrival of winter ice, which threatened to delay the installation for 5 months and bring heavy financial penalties. Audio. As temperatures dropped and chunks of ice began to flow down the river, the risks multiplied. Barges carrying the 1,000-ton arch could easily be damaged or trapped. Ice buildup on cables added unpredictable weight and strain, raising fears of catastrophic failure. Workers described the constant pressure. They were in a race against time, and nature was the opponent. With the freezing season advancing, the crew waited anxiously for the decision on whether conditions were safe enough to proceed. Finally, in the early hours of the morning, they received approval to make the critical move. Clad in full survival suits in case of accidents on the icy water, the crew prepared for the operation. Winches pulled the barges forward slowly, often no faster than a meter per hour, while teams ashore adjusted guides and skid shoes to receive the arch. The ironworkers modified steel supports at the last moment to ensure the span would sit securely when lowered. On the barges, men worked in freezing winds, handling cables and guiding the enormous structure with millimeter precision. The operation was tense, with everyone aware that one mistake could mean disaster. Yet, as the hours passed, the arch floated steadily into position. The final stage was the most nerve-wracking, aligning the arch between the two towers. Engineers and ironworkers worked side by side, calling out adjustments, nudging the span into place. At last, with a collective sigh of relief, the structure touched down on its bearings. Welders quickly secured it, transforming months of planning and days of struggle into a solid reality. It was an exhilarating moment, proof of what teamwork, determination, and courage could achieve under extreme pressure. Life on the site was not only about stress and danger. The workers brought humor and camaraderie to the project, sharing jokes, teasing each other, and finding ways to lighten the mood. They knew that laughter could ease the strain of long, freezing days and constant deadlines. At times, they even found small distractions, like rescuing a bird frozen to the ground, as a reminder of the human spirit that thrived even in the harshest environments. Despite the difficulties, the Walterdale Bridge project was more than just another construction job. It symbolized renewal for Edmonton, replacing a worn-out bridge with a landmark that reflected modern engineering excellence. For the ironworkers, it was also deeply personal. Every bolt tightened, every weld completed, and every dangerous climb represented their craft, their pride, and their legacy. To them, the bridge was not only steel and concrete, it was a monument to resilience, skill, and the willingness to face fear head-on. When the final welds were completed and the barges withdrawn, the most difficult part of the job was done. Although work remained to finish the bridge, the successful installation of the massive arch was a victory that belonged to everyone on the crew.